What's going on here? All right, so we're going to continue with where we left off last time. We were trying to express functions as power series. And I have another example for us. Right here. So remember that the whole goal up to this point was to try and use this formula, and that's about all we had. And we saw last class that it could just be right here in the problem that you can massage it and make it look like that formula, which is like the quiz problem. Or in last class at the end, I showed you that sometimes you have to look at it and go, oh, wait, that looks like the derivative of something that looks like that, or that looks like the antiderivative of something that looks like that. I showed you two examples, one of each. And then we did like term-by-term integration or term-by-term differentiation. Now, so this one, we have to try and figure out, does it look like that right away? Is that the derivative of something, the integral of something? And we can mess with this for a while, trying to figure it out. The thing is, each of these denominators by themselves would fall into that category, wouldn't it? But the fact that they're multiplied together creates an issue, right? There's a product there. So I can't, we already talked about the product of two infinite sums is not easy to resolve. So what I'm going to do is partial fractions. I'm going to use partial fraction decomposition first to try and split this up into two terms. And I'm not going to show the work for the partial fractions because we've done it so many times. That we should all be at least comfortable with the idea of what I would do to get to the next line. So the next line would require some work, but we would get it to, and you'd have to work this out yourself, 1 over x minus 1, and then minus 1 over 2x plus 1. So if you believe that that would turn into that, then we can proceed. Each one of these individually looks exactly like something over there with our formula. We just have to kind of, again, massage it, make it look like what's over there. So on the first one, 1 over x minus 1, I just need the 1 and the x to switch places, right? So what I'm going to do is just factor a negative out of the bottom and place it on top. So this is the same exact expression. And then on this one, what should I do? We need a 1, don't we? And then minus an x. So I have a 1, don't I? But then I need minus the x term. So how about minus negative 2x? Wouldn't that be the same thing? So in each of these, the highlighted in yellow is the x part of the geometric series formula. Do you agree? I do have a negative 1 on top of the first one. So I'm going to pull that out. So here's where we are. We have equals negative 1 times 1 over 1 minus x, then minus 1 over 1 minus negative 2x. Any questions on that part? Again, highlighting the part that's going to become the x in the formula. So each one of those, when I say those, I mean this and this, can be rewritten using the summation over there, right? So let's do that first one. We have the negative. I'm just going to put a negative. I won't put 1. And then what is that 1 over 1 minus x as an infinite series? We got sum, right? N equals 0 to infinity of x to the n. That's it, right? So long as what? That's true. This is true so long as the absolute value of x is less than 1, right? So I'm going to put that over here. I'm going to have absolute value of x has to be less than 1 for that first one to work, correct? Now what about the next one? Minus sum n equals 0 to infinity of what this time? Negative 2x, that entire quantity to the n. And that's true as long as what? Absolute value, negative 2x less than 1. Now, the instructions here are to write this as a power series. And remember that a power series, all power series, are going to look like, I'll put it right, whoa, I didn't see that. Sum n equals 0 to infinity, c sub n, x minus a to the n. That's what we mean by a power series. And that means that it needs to be a single summation, not two sums added together. So we need to somehow put these two sums together, all right? And the good thing about sums is that if you have two infinite series added or subtracted together, you can just put both of the expressions in the series together through addition or subtraction, and create one sum. That's, as long as they converge, that's true, and these converge because we are assuming that the x's fall within this range. All right, so my next line is going to look like this. I'm trying to figure out what we want to do with that negative. How about we do this? Sum n equals 0 to infinity, negative x to the n minus negative 2x to the n. So all I did was I put this negative inside here with this right there, and then this negative, I put it inside, well, I just left it, sorry. And then this right here is here. Do y'all agree? Same thing? Okay with that? And cleaning up a little bit more, I would like to get a single expression for x, just like in the power series representation over there. I'd like a single factor of x to a power. Right now I have these are split up. So let me first resolve this right here. Negative x to the n minus, how about negative 2 to the n, and then x to the n. That's the same thing, right? And since these both have an x to the n and an x to the n, I can factor an x to the n out and place it at the back of the expression like this. And just tell me what would go in here. Negative 1. Now be careful because that negative right there does not have the exponent on it, or else I would have had to put it in parentheses. Remember, the negative came from being out here. So that negative is not changing sign. It's always negative, right? So we just leave it as a negative 1. Does that make sense? That's what you get when you factor x to the n out of this. And then when you factor x to the n out of this, what are you left with? Minus negative 2 to the n. And that's it. That's your power series. You have your c sub n right there, and then you have your x minus a to the n here. You could probably do some stuff with this and clean it up and somehow work with that negative sign. And so the answer, like in the back of a book, might look a little different, but they both create the same series, so that would be okay. Remember that with sequences, there's multiple ways to represent a sequence. You can create a sequence. I can create the same sequence you create, but our formulas can look a little different. So this is fine as long as it's doing what it's supposed to do. And then this part right here, or x to the power. We do need to state the interval of convergence, and that came from back up here, right? So let's go through here and figure out what our interval of convergence is. We don't want to state two separate intervals. We want to see if we can break that down to just one answer. Because remember, it's going to have either an interval, a point, or the whole number line, right? Those are the only three possibilities. So we can't have two different intervals. So this one says the absolute value of x has to be less than 1. That tells us that x has to be between -1 and 1. That's one possible answer. And then the other one, this is the same as 2 absolute value of x less than 1. And dividing both sides by 2, absolute value of x has to be less than 1/2, which means that -1/2 has to be less than x has to be less than 1/2. We talked about that at the beginning of class last time, or when we first started this. So in order for the blue one up here to converge, we've got to be between -1 and 1. But for the green one to converge, we have to be between -1/2 and 1/2. So to get them both to converge at the same time, we're going to need to use which one? The 1/2 one, the smaller one. We can't go outside of that, or else the green one won't converge. So our interval of convergence, I, is going to be -1/2 to 1/2. We do not need to check endpoints because it's a geometric series. So we're done. Understand? Okay, now, next one. This will be our last example for expressing as power series, and probably the most challenging one. Find the interval of convergence after you express this as a power series. All right, so 2x squared plus 2x over 1 minus x cubed. All right, you ready? So I'm going to go to last class, take a look at one. See, it was after this one. No, it wasn't that one. Okay, so I had introduced this idea of that if you have a power series, then the derivative, remember this thing where I said the derivative is basically the power rule, but you have to change the index? And that the antiderivative is basically the power rule for integration, but you don't have to change the index, but you have to throw a constant in there. And then after I did that, I did this example where we looked at this and we said, hey, look, that does not look like this geometric series because of the squared. And we said, remember this? Aha, but this is the derivative of this? Yes? Yeah? Yeah? Okay. So 1 over 1 minus x squared is the derivative of 1 over 1 minus x. With that in mind, we look at this and we say 1 minus x cubed is actually connected to that also, isn't it? How is it connected? It's the second derivative, but I think we might be off by a constant or something. We'll have to see. So we have to recognize that the 1 over 1 minus, the 1 minus x on the bottom cubed is the derivative of this. So I think it would be useful for us, since it's probably going to come into play later, to write out what the derivative of this is. So 1 over 1 minus x, right? What's its first derivative? What's the derivative of that with respect to x? So we did this last time. It was 1 over 1 minus x squared, right? That's what that is. Now, what's the derivative of this? So what's the derivative with respect to x of 1 over 1 minus x squared. What's the derivative of that? So maybe it'll help if we rewrite it as 1 minus x to the negative 2. Then bring your negative 2 out. We're taking derivative now, right? Take the negative 2 out. Negative 2, 1 minus x, chain rule to the negative 3, times the derivative of what's inside, which is negative 1. So this equals, what could I say, 2 over 1 minus x quantity cubed? Yes? Which is why there's a 2 on top. I did that intentionally to help us to keep our math a little clean. There it is. Okay? So we're recognizing now that, look, that 1 minus x cubed on the bottom is connected to the second derivative of the geometric series that we know. So to do this, we're somehow going to have to work with this second derivative and then get it back to where it came from. All right, now on the top, we have an issue because it's not a 1. So what I'm going to do first is split this into 2 separate terms because I have the same denominator in both. I can do this. We agree. That's just splitting it up. And now, you see the 2 up there? So nice that that 2 is there. Because I can write x squared, pull that out, and then 2 over 1 minus x cubed, and then plus x times 2 over 1 minus x cubed. You with me? Good? All right. I need to pause in this and address the 2 over 1 minus x cubed. So note that, or I'll say notice that the derivative with respect to x of 1 over 1 minus x, I'm thinking if I want to do it this way or not. Yeah, I'll do it this way. Do you agree with that statement? Yes? And do we know what this is? Do we know what this is as a power series? Well, yeah, you have to go back to your notes, though, and you have to look at what we did. And look, didn't I give you this problem already, and I said, write this as a power series? And we went through all this work to do it, right? Okay, I'm skipping this step, but that's what you would have to do here. You would actually have to go do this and come up with the power series, and I believe this is what we got, right? This was our answer? Right here. So I'm going to paste that answer into our problem now. Okay, we should have the sum n equals 1 to infinity, because we had done a derivative, so it changed the index from 0 to 1, of n x to the n minus 1. All right? So right here, this will be equal to the derivative of, so you notice I'm not taking in a derivative, right? I'm just doing a direct substitution. What is this thing? We just said that it is the sum n equals what? 1 to infinity of n x to the n minus 1. That's what this is equal to. Do you appreciate the amount of work that that would have required? I mean, it's not like a day of work, but do you understand that would take you, 10 minutes maybe to get that piece? So I'm trying to rewrite this as a power series, and I know right now that it is exactly equal to the derivative of this power series. And what is the derivative of this power series? So how do you take the derivative of a power series? What do you want to do? Okay, so bring the power down, subtract 1 from the power, and then what would happen to the index? It would go up, wouldn't it? Wouldn't it go up? Okay, so we could do the derivative of this right now. I'm going to do something. I want to see if you follow this at all. I'm not going to do that derivative yet. Just see if you're comfortable with this. You tell me what I've done here. Sum n equals 0 to infinity n plus 1 x to the n. Okay, what did I do here? I didn't take a derivative. What did I do? I shifted the index. In other words, I said before, remember with the geometric series, the one that we had started with, n started at 1? But I said if we wanted to, we could start at 0, and here's how you do it. I showed you that last class. That's what I just did. And I'll show you on the side what I did. I'm replacing n with n plus 1 in this expression right here. I replace that n right there with n plus 1. I do that because if this side is n plus 1 equals 1, n plus 1 equals 1 means n equals 0. I could subtract 1 from both sides. But if I replace this n with n plus 1, I have to replace this n with n plus 1 and this n with n plus 1. That's what I did. And that gives me this. So now let's do a derivative. What is the derivative? Oh, I'm taking the derivative now. What's the derivative of that series? It's going to become sum n equals 1 to infinity of n times n plus 1 x to the n minus 1. That is what this is equal to. So there I took the derivative. So I ignored the n plus 1. I applied the power rule. The n came down. I subtracted 1 from the n, and the index went up by 1. There. You could have done it from up here and just changed the index to 2 if you wanted to, but this is the way I chose to do it. All right. At this point, I'm ready to go back up to this now. All right? This right here. I'm ready to rewrite this line. I'm going to grab this line. And I think I'll start it on a new page. So I'm continuing now. This should be equal to x squared times, what was this series here? Sum n equals 1 to infinity of n plus 1 and minus 1, right? And then what was the next one? X times the same exact series, isn't it? So all I did here was replace this and this here and here, right? Now we want to try and put this all together at some point, but let's take care of the x squared. Can I push the x squared into this? Yes? Yeah, because there's no n on it, right? So I can just put it inside. And what happens when I put x squared next to x to the n minus 1 and multiply them? What do? Add the exponents, right? So what's n minus 1 plus 2? N plus 1? So you're going to get sum n equals 1 to infinity of n times n plus 1 times x to the n, what do you say? Plus 1. Yeah, so n minus 1 plus 2, so n plus 1. We good? Questions? What does this next one become? What's our power on x here? X to the n. Okay. Now, any questions up to this point? This next part's going to be a little bit tricky. All right? We want to put these two together, right? We want to put these two together. But what we want is for this x to the n and this x to the n to be the x to the n plus 1. We want those to be to the same power. And the reason we want them to the same power is because we would like to be able to factor it out so that we can get that x minus a to the n part for the power series. So in order for me to ever factor this out, they have to look the same. Do you understand what I'm getting at here? Let me write down, don't write this down, let me write down, if you try to put these all together right now, right, that's what you would have if you put them together now. Do these both have an x to the n in them? Yes, so you could factor an x to the n out. I'm going to factor it out here, and then it's gone. And actually, this one is gone, but what's still here? There's still an x here, right? And now you would think you're there, but what's the problem with this? This right here, right, has your variable. This is your x minus a to the n. This is supposed to be your sequence c sub n, but what's in it? X. You can't have an x in your c sub n. Your c sub n is supposed to be a constant, isn't it? And it contains a variable. This is not going to work to get it to look like a power series. So that's why I said this next part's tricky. Okay, so how in the hell do we do it? What we do is kind of what we just did a second ago. Remember when I changed the index over here? I said, I'm going to get this back to 0 just because I wanted to, you know? I'm going to do something similar to that. I would like for this one to not be n plus 1. I'd like for it to just be n. So if I replace n with what, I could make this an n. N minus 1. Do you agree? So I'm going to come in here, and I'm going to make a replacement. I'm going to let everywhere I see an n, I'm going to replace it with n minus 1. I'm going to do that in the entire summation. And let's see what we get. Sum, I'm going to place n minus 1 equals 1 to infinity, n minus 1, n minus 1 plus 1, x to the n minus 1 plus 1, and then plus the other one I'm not touching. I'm just going to leave it. Oh, no, you can't. And that will be another issue we'll have to address in just a second. Okay? Y'all okay with that? All right, let's go ahead and rewrite this blue one. It's going to be somewhere. N equals 2 to infinity, n minus 1 times n times x to the n, plus the other one. Okay. Y'all still with me? Yeah? So now I've somehow miraculously made these both x to the n, so I'm very happy about that because when I put them together now I could factor x to the n out. Wouldn't have any x's left behind. But as was noticed, these series do not start at the same place now, right? They don't start at the same, the index doesn't start together. So you can't add these together directly because they're not starting at the same place. But anyone have an idea of how I can resolve that? All right, so let me ask you. If I'm supposed to add these up, right, forever, the first thing I do is I plug in 1, don't I? And then put what? Plus, and then I plug in 2, and then I do plus, and then I plug in 3, and then I do 4 and 5 and 6, right? So let's plug in 1. What do you get when you plug in 1? 1, 2x, yes? I'm going to do this in black so you'll realize where it came from. 2x plus, now I'm supposed to do the next one, right? Plug in 2, and then plug in 3 and 4 and 5 and 6. So why don't I just, instead of writing each of these out, why don't I just tell you to start now at 2 and continue the rest of the way? Essentially, I just peeled the first one off, right? I just peeled the first one off and said, okay, now go from 2 on forever. And so the 2 series at the ends now start at the same place, but you had to peel that first term off. And so I will write equals, I'll put the 2x way out here, plus, now I'm going to combine those 2 series together. And then what goes in here? So I'm combining all this junk with all this junk, right, together. And I will factor an x to the n out of both, and I'll stick that on the end. So what is the thing in here? What goes in here? Okay, n minus 1 times n, and then what's plus, okay, n times n plus 1. Do y'all see these 2 series I can put together now because they start at the same place? So you just combine the actual sequence definition inside of each one together with addition, because there was a plus here. That 2x I just dropped out front. And you could actually clean this up too, right? This is n squared minus n. This is n squared plus n. So that just gives you 2n squared. We good? Understand? It's a lot of work, right? So let's see. If we plug in 2 here, what would we get? If we plug in 2, we would get 8x squared, right? Pardon me? Plus the 2x, right? This 2x is always out here. This would be fine on a test if you box this up, but I want you to see something. I know it doesn't say plug in 1, right? It doesn't say plug in 1, but what would happen if you did plug in 1? What would you get? 2x, wouldn't you? So, I mean, I could if I wanted to, because this guy right here just happens to be what you get when you plug 1 into this. I could actually write it this way. But it's purely coincidental that it works that way. See, I changed my index to 1 because when I do plug in 1, I get that 2x. Do y'all understand that? It worked out that way. So this is our power series. Right there. Our C sub n, I'm out of room. This is our C sub n. This is our x minus a to the n. Now it starts at 1, right? I could make it start at 0 by replacing all my n's with what? N plus 1. N plus 1. And I could start at 0 if I wanted to, but this is fine. And now we never got the interval of convergence. We never got that. But if you go back, well, here, let's see, remember when we were doing this part, I said you had to go back in your notes you go back and look at your notes, we used the geometric series. The x part in the geometric series that we used in this case is just x. So it'll be just absolute value of x less than 1. So our interval of convergence is still negative 1 to 1. I is negative 1 to 1. Bam. Now that is a great problem right there. I mean, there's so many things involved in that problem that are subtle that you have to pay attention to. So that's what makes it such a great problem. All right. I gave you homework out of 8.6 already? Did I? 8.6. I think I did. I gave it to you and I said, I don't think you can do this, but if you want, you can get started. Is that correct or no? Maybe not. What, for what? Page 474, what did I give you? 3 to 11 odds. And then what? Yes. Okay, so that's correct. For those of you who may have come in late, we took a quiz. And then also the homework 8.3, 4, 5, 6, and 8.7. Each of those I've given homework assignments for. On the day of the final, which is next Thursday, I'm asking you to bring those in, your homework, and just an honest attempt at each of those homework assignments. Doesn't have to be perfect. Next Thursday, a week from today. And just have those, and I'll give you a quiz grade for each one. So that's going to account for, what, 5 quiz grades? For each one of those? 8, 6? I don't know. What was it? 3 through 11 odd? 15, 17, 19? Okay. Page 474. All the other ones should be in the notes. I mean, I put the other assignments up. If you are having trouble finding the homework assignments for those, then you should have been doing your homework, number one. But your classmates, I'm sure someone wrote it down. All right. Okay, 8.7, we're moving on. Taylor and Maclaurin series. All right, here we go. Suppose, that's the symbol for suppose. Have I shown you all that one? Yes? Okay. Suppose you have a function that happens to have a power series representation. Where we also have some radius of convergence. So what we're saying is that you have a function, it can be represented as a power series, and it converges on an interval as opposed to converging at a point only, all right? We know that f of x, if we expand that power series out, is c sub 0 plus c1 x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a cubed plus c sub 4 x minus a to the 4th plus dot, 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 right? That's what that function would look like if it was expanded out. Yes? The question, okay, the question that came up that Newton attacked was that if you've got the power series, if you know that a function can be represented this way, right? Then the only thing we really would have to figure out is what the constants were. If I knew what the constants were, right, then everything else is always going to be the same. It's always going to be the constant, c sub 0, then it's going to be x minus a to the first power, then to the second, third, fourth, regardless of the function, right? They're always going to have the similar power thing happening. But the constant's the thing that's really dictating what this is going to look like. So how do we find the constants became the question, all right? So how about this? Let's try to find c sub 0, c sub 1, c sub 2, without me giving you a function. So I'm not going to even give you like an example of a function to use. Just in general, can we figure out what those are? So here's where things, this is just, I think this is beautiful. Watch. First thing, let's let x be a. Okay? Let's let x be a. What would happen if we plug in a for x? What would f of a be equal to? So go in here, place all your x's with a's, and tell me what you'd get. C sub 0. Wait a minute. You mean to tell me that if somebody gives me a function, like let's say sine of x, and I want to represent it in its power series, then I'm going to need to be able to first figure out that first constant, I'm just going to need to be able to plug a, whatever a is, it might be, you know, pi over 2 or something like that. I just need to plug that into the function, and that would give me my first constant. Yes? Okay, fine. How about this? We know what the first constant is. Great, let's try and find the next one. How about this? What is f prime of x? Tell me what the derivative of this up here is. What's the derivative of this? So what happens to this constant? Goes away. What's the derivative of this? C1, and that's it? Plus, okay, now let's pay attention to this one. Because of the power up here of 2, we'd have to bring that down, right? This would become 2c2 x minus a to the first power. The next one would become, what, 3c sub 3 x minus a to the second power. What's the next one? 4, right? C sub 4 x minus a cubed. And then plus, I'll do the next one just because I have a little space and I want to see if you understand the pattern. What's the next one? 5. Oh, sorry, I forgot the c sub 5. X minus a to the 4th plus dot, dot, dot. All right, fine. That's what the derivative is. Why in the world did I do that? Because now what I'd like for you to do is find what f prime of a is. What's the derivative at a? C1, isn't it? Isn't it C1? Hold on a second. So I know how to get C2. I just plug a into the function. I know how to get, wait, what did I just say? I know how to find c sub 0. Did I say C2? Okay. I know how to find c sub 0 by just, all I have to do is evaluate the function at a. In order to find c sub 1, I just need to be able to evaluate the derivative at a, right? And how are we going to find c sub 2? What do you think we should do? Take the derivative again. Yes? So take the derivative again and tell me what the derivative would be. Now we have to pick up on something subtle here. It's very important, all right? See what happens when we take the derivative. 2c2 plus what? 6c3 x minus a? I don't want you to write 6 though. I want you to write this. 2 times 3, c sub 3, x minus a. What's the next one? 3 comes out, but again, let's not write it as 12. Let's just write it as 3 times 4, x minus a squared. Do y'all see it? What's the next one? 4 times 5, c sub 5, x minus a to the third plus dot, dot, dot. So how am I going to get c sub 2 now? Plug a into the second derivative, right? Plug a into the second derivative, and I would get just 2c2, wouldn't I? And let's solve for c2, because right now I have a 2 in front of it. So wouldn't I just divide both sides by 2? I'll do it next line, which means that f double prime a over 2 equals c sub 2. Let me start highlighting our answers here. That's c sub 2. Here was c sub 1, c sub 0. I think we're going to have to go at least one more for you to see the pattern. What would I do now? If we're going to continue the same process? Another derivative, right? So I could do triple prime, but there's a better notation whenever we need to take a lot of derivatives. And that's putting the derivative as a number, but we have to put it in a parenthesis. Have you all seen that before? Cal 1? If you just put f to the third without parentheses, that means you're taking f and multiplying it times itself 3 times, like cubing the function. But if you put a parenthesis around the 3, that means third derivative. All right, so what would our third derivative be? So derivative of this up here. This is gone, right? That's a constant. What's derivative of this? 2 times 3, c3. Plus, now this is the part that I'm hoping you'll pick up on. What's the derivative of this? 2 times 3 times 4. Oh. X minus a to the first power. What's the next one? 3 times 4 times 5, x minus a to the second power plus dot, dot, dot. What are those looking like in front of those? They're looking like factorials, right? In fact, I know that when I now plug a into this derivative, because that's what we've been doing, everything here is going to vanish, right? And the only thing that's going to be left is the 2 times 3. And the next time I do it, right, the next time I do it, what's going to be, oh, I forgot something in here on both of these. Geez, what am I missing here? Sorry, c sub 4. Nope, that was an oversight. X minus a. This one right here, right in here, c sub 5, right? So let me go back to that. When I plug in a right now, everything out here goes away. I'll have 2 times 3, right? Isn't that the same as 1 times 2 times 3, right? 1 times 2 times 3 is 3 factorial. So it looks like what I'm going to get is a 3 factorial out here. Now, aren't I going to have to divide it out? Yes? Up here, this 2 that we were left with in front of the c sub 2 is 2 factorial, isn't it? And then right here, what was in front of this one? That we didn't realize it then. 1, which is actually a 1 factorial, right? So look, first derivative, I had to divide it by 1 factorial. Second derivative, I have to divide it by 2 factorial. Third derivative, I have to divide it by 3 factorial. What about the original one, though? That's 0 factorial, isn't it? The 0th derivative is don't take a derivative at all. And so you're going to wind up dividing by the 0 factorial, which is 1. So it looks like we're getting a pattern and that this thing's always going to work this way. I'm just going to go and plug this in now. The third derivative at a is 2 times 3 c sub 3. And that means that f triple prime a divided by, I'm out of room, 2 times 3 equals c sub 3. Do y'all see the pattern? Because if you see it, I'm ready to go right to the formula. Yes? All right. Therefore, C sub n should always be equal to the nth derivative at A, right? The nth derivative at A divided by what? N factorial. And this is for n greater than or equal to 0. Of course, n is an integer, but this formula works for 0. All right. Now, this is what's called the Taylor series. All right. It is super powerful, but it requires us to be able to do something, and that's take derivatives, right? So this will work. This works if f of x has, I want to see how the book says it, I forget, n derivatives or something like that. Hold on. Yeah, doesn't say it. Okay, yeah. Has n derivatives. That means you have to be able to differentiate the function. There are functions in mathematics that are not differentiable. And so if your function fails to be differentiable, this formula is not going to work because you have to have derivatives to use it, right? So as long as the function is differentiable, we can apply this formula. And so here's the final conclusion. If f of x has a power series representation and n derivatives, then f of x can be written as the sum n equals 0 to infinity x minus a to the n out here. Now, we said that if it has a power series, that it's going to have a c sub n right here, right? And we just found a formula for c sub n. The formula is the nth derivative at a over what? N factorial. And that's big time right there. That is big time. Because now, give me a function, I give you the power series, as long as I can take derivatives. As long as I can take derivatives, I'm in business. All right? So let's look at an example. That formula should probably be memorized. It's that important. It's just one of those things. It's like, if you're ever going to use a power series on a function, you should know. I mean, this part's pretty easy, x minus a to the n, because we've been using it so much. This right here, nth derivative at a divided by n factorial. That's all you got to really remember. And of course, if you forget it, you can always derive it, right? You can always just go back through and derive it. In fact, that's the way I do it. I mean, I don't know if I'm sure if I thought about it hard enough, I could have told you that formula, but I always trust that I'm going to get it if I just derive it. So there's a difference, I guess, between knowing and understanding something. You know something, you memorize it, versus understanding it, which is a little deeper. All right, example time. We call that, right there, I need to go back and tell you what this is called. This is called the Taylor series of F centered at A. All right? So in the next one, this example, find Taylor series of f of x equals x squared plus x plus 1 centered at 1. Now, this first example is purely to get you to see how to use the formula. That's all it's about. The function I'm giving you, this is a very simple function, isn't it? It's a polynomial. In fact, isn't that a power series? It is. So we would never, well, let's just see what happens. Maybe your gut's telling you that our answer should be very similar to what we started with, because we're trying to find a power series for a power series already, right? It just has a bunch of zero terms, doesn't it? Like a 0x cubed, 0x to the fourth. They're not there, are they? Okay, so maybe it'll work out. Let's see. All right, so let's figure out what some derivatives are, because we're going to need all the derivatives, aren't we? So I'm going to start by writing out derivatives. What is the zeroth derivative of this function? What is the zeroth derivative? Itself, right? Good. Okay, now remember that in the formula, we need the zeroth derivative at A, don't we? The zeroth derivative at A? Okay, so what's A here? 1. And so now plug 1 into this and tell me what you get. 3. Okay. Now, next part. First derivative. First, what's the first derivative of x? Of this function at x? 2x plus 1. Now, after you've taken the derivative, plug 1 into it, and what do you get? 3. Yes? Now, take the second derivative. What's the second derivative of this thing? 2. And now plug in 1 into that, and what do you get? It doesn't do anything, right? 2 is a constant, so you just get 2. Now take the third derivative. What's third derivative? 0. And now plug in 1 into that, and what do you get? 0. Do you understand what I'm doing? Now, what's the fourth derivative? Same thing, 0, 0, 0. So from here on out, aren't I going to get zeros the rest of the way? So what I'm going to say is over here, f n1 will equal 0 for all n bigger than or equal to what number? From 3 and on, right? So what I'd like us to do now is write out the power series. So f of x should be equal to sum n equals 0 to infinity, the nth derivative at a over n factorial x minus a to the n, right? That's what this function should be able to be written as. Yes? All right, so let's start out with n equals 0. If n is 0, what was the zeroth derivative at 1? Because a is 1 for us. What's the zeroth derivative at 1? It was 3, right? It was 3. I want to divide that by what? 0 factorial. So I'm going to put over here 3 over 0 factorial, and then x minus what? 1 to the 0th power. I'm just showing you everything plugged in instead of actually just writing it out. I'll do it on the next line. Plus, what's the next one? So now I plug in 1, I get 3 over 1 factorial, x minus a, or x minus 1 to the 1st power, right? Next one. 2 over 2 factorial, x minus 1 squared. And what's the next one? 0. And the next one? 0 forever, right? Get that 0 forever? And so we get, what's this first one here? X minus 1 to the 0 is 1. 0 factorial is 1. So that's just 3, isn't it? Okay, this one right here, x minus 1 to the 1 is x minus 1, but then there's a 3 out in front of that. So this is plus 3 times x minus 1. And then finally, here, x minus 1 squared, but then in front, 2 over 2 factorial is just 1, isn't it? So this is plus x minus 1 squared. Yes? And just for kicks, let's just multiply this out and see what we get. What do we get? Do y'all agree with that? Yes? We get x squared plus x plus 1, yeah? Which is the original function. Which meant that the Taylor series of a polynomial function is the polynomial function itself. And that kind of makes sense because we're saying, look, I'd like for us to get some idea, all right, let me try and help you see this in a bigger picture. We have a function, and we are trying to figure out how this function behaves near 1. So we're trying to figure out a power series that will help us figure out the behavior of this function near that value of 1. And the formula for the Taylor series says, you know what? Here's the candidate. Here's what we're going to use. We're actually going to use this power series, which happens to be the same function because the function was a power series. Understand? What if that original function that we start with is not a power series, though? It's not a polynomial. Then what will this formula lead us to? All right? Yeah, I think we're ready for this one. One more note, though, a quick note. If we take a Taylor series centered at zero, then we have the following formula. Our function would be sum n equals 0 to infinity, nth derivative at 0 over n factorial, and then what? Just x to the n, right? Because a is 0. So you take the Taylor series and just replace a with 0, right? This right here happens so much, or we use this a lot, where we center it at 0. that it has a special name, all right? And this is called the Maclaurin series. So basically, a Maclaurin series is a Taylor series, but it's a special one. It's the one where A is 0. If A is something other than 0, then you call it something other than a Maclaurin series. You call it a Taylor series. So Taylor series, bunch of different possibilities. Maclaurin is one specific example of a Taylor. Have you all ever seen, was it Good Will Hunting? The one with Matt Damon where he's like a math genius. Have you ever seen that? If you've seen it, there's a scene where he had done some problem and he gave it to the professor, and the professor's like Matt Damon like lights it on fire. You know, it was like, this is easy, and he lights it on fire, and the guy's like, please don't burn it, whatever. Anyway, when the professor is reading Matt Damon's work, they don't show the work, but he says in it, he's like, oh, I can see you use Maclaurin here. That's basically what it's referring to. So this is used, I mean, it is used in math a lot, Maclaurin, all right? The fact that they use it in a movie is just, you know, reaffirms the fact that it is useful, all right? So let's see this in action. I think it's time to do a non-trivial function. I'm hoping that this is going to be enjoyable to see. I can't predict. With all the joy I get from you every class, I'm not sure if this is going to overload me here. Oh my goodness. All right. Find Maclaurin series for f of x equals cosine x, cos x, whatever. So we want to kind of start to establish a pattern, the way we're going to do these things. I'm going to first look at it and ask myself, can I take derivatives of that? Sure. I know what derivatives of those are. And because it's a Maclaurin series, I know I'm going to be letting my A be 0, right? Yes? A is 0. So let's start taking derivatives and then plugging in 0 into those derivatives and seeing what we get out. So how about the 0th derivative? What's the 0th derivative of this function? Itself. And then, do we know what the 0th derivative is at 0? Yeah, cosine of 0 is 1. Okay. Now the first derivative. What's the first derivative of cosine? Negative sine of x. And there, when we plug 0 into that, what is the derivative? What is negative sine of 0? 0. All right. Second derivative. What is the derivative of negative sine x? Negative cosine x. And what is 0 plugged into negative cosine of x? Negative 1. Third derivative. Third derivative of negative cosine was what? Sine. And then you plug 0 into that, you get 0, right? Now what happened for us in the previous problem is eventually we knew that all those derivatives were 0, right? So we could kind of stop. Here, we're just going to keep derivative's never going to go away. It's always going to keep giving us something, right? But as was stated here, there's now going to be a repeat in this pattern, isn't there? The next one's going to be the fourth derivative, sorry, is what? Cosine. And we already know, I'm going to go through all this, we already know what happens when we plug 0 into this. What do we get? 1. And then the fifth derivative, we already know what's going to happen here. It's going to give us 0. Yes? And then the next one, the sixth derivative, will be -1, and I'll do one more. The seventh derivative will be 0, and then repeat again. Yes? How could we state this in a nice, clean format, just what's happening here? What can you tell me about the nth derivative at 0 for this particular function? There are, 3 possible answers. It's 1, -1, or 0. When is it 0? Tell me when it's 0. Anytime the derivative you're taking is what? Odd. Do you agree? So I'm going to put it 0 if n is odd. Now, when is it 1? I'll highlight it. When is it 1? At the 0th derivative, at the 4th derivative, at the 8th derivative. Aren't those multiples of 4? Yes? So I could say if n is a multiple of 4. Have y'all ever seen modular arithmetic? Okay, let me show you an example. I'll do it on the board over here, because that, in math, we don't like to say if n is a multiple of 4. We have a better way of doing it. Okay, so look, let me just take a number like, if I say 4 mod 2. What this means is you take 4, divide it by 2. How many times does 4 go into 2 go into 4? Twice, with the remainder of 0, right? You always put what the remainder is after the division. So 4 mod 2 is 0. What's 5 mod 2? So how many times does 2 go into 5 evenly? Goes in there twice, right? With one remainder. So 5 mod 2 is 1. Understand? What is 7 mod 3? 1. Understand? What is 7 mod 5? 2. Y'all understand this? So a better way of writing this, n is a multiple of 4, is to say that, I'm going to scrap it. I'm going to say that n mod 4 must be what? 0. Would that mean you're a multiple of 4? As long as n mod 4 is 0, you're good to go. Now, what about this -1? Where are you getting -1s? At what, 2, 6? What would the next one be? 10? Could we do this with the mod? You need that n mod 4 not to be equal to 0, but to be equal to what? 2. So like, think about it. 6 mod 4 is 2, right? 10 mod 4 is 2. Question would be, what's 2 mod 4, right? Oh, yeah. It worked the same way. Two mod 4 would be 2 still, because how many times does 4 go into 2? It doesn't. So how much is left over? The 2 you started with. So, understand? How could we say evens instead of this way? Could we do it with odd? Three, 5, 7, 9. What do those all have when you mod 2 them as a remainder? 1. Okay, that was just, sorry, I went off on a little tangent there. If you wanted to write yourself like in words, that would be fine, but mod is the preferred way to go. I always remember this when I was in graduate school. You do a lot of mod stuff later on, and I was really, really tired one time, and I had to get up and go to class. And like, when you're like in half dream, half reality state, I was like looking at my clock, and I actually was doing some mod arithmetic on the digits and convincing myself that it wasn't the time it was. It was because I was doing so much math at the time, my brain was still doing math, and so I look at the clock and I'm like, no, that's not really 7, that's really like 1. I was like, I was so messed up, man. So tired. Okay, now, we're not done with this problem, right? We have a pattern here. So let's now set it up. Let's write out what the series is and see if we can actually come up with this Maclaurin series. So cosine of x should be equal to the sum, n equals 0 to infinity, of the nth derivative at 0 over n factorial, and then it's just x to the n because we're doing a Maclaurin, so it's not x minus a. So let's start. At 0, what did we get for this top piece right here? At 0, it was 1 over 0 factorial, x to the 0. That's what we get when we plug in 0. Of course, that's just going to turn into 1, but again, I'm trying to show you where everything's coming from. Plus, now we plug in 1. What was the first derivative at 0? Well, that's an odd number, right? Odd number? We know that gave us a 0, didn't it? 0 over 1 factorial x to the first power. What's the next one? So we're plugging in 2, right? That's an even number, but it's the mod 2 one. So we're going to get 1 out. Was it, no, -1, right? -1 comes out, and then on the bottom, be careful here. 2 factorial, and then x to the second power. Yes? Next one. 0, because it's odd, right? 3 factorial x cubed. Next one. Now we're at a multiple of 4, mod 2. It's getting a 0, so what is it? 1. So we're going to go 1 out. If you look at the tops, here's our pattern. We got 1, 0, -1, 0, so now it's going to repeat itself. So 1 over 4 factorial x to the 4th. Next one, 0 over 5 factorial x to the 5th. Next one, -1 over 6 factorial x to the 6th. And we could keep going, couldn't we? Yes? Now, I'm going to cancel out the ones that are going to be zeros. This is gone, and this is gone, and this is gone, right? And then I'm going to really clean this up. The first term is 1. What is the next term? -1/2. Okay, as long as you remember that came from 2 factorial, right? The next one, plus 1 over, and you know what, I'm going to leave it. I don't think we're ready for it. 2 factorial, this is 4 factorial, right? X to the 4th. Next one. Minus 1 over 6 factorial x to the 6th. Now, we didn't write more of them out, but let's see if you can predict what the next one's going to be. Plus or minus? Plus 1 over 8 factorial x to the 8th. Next one, minus 1 over 10 factorial x to the 10th plus dot, dot, dot. Yes? Yes. Write it as a series now. Write it as a series. Sum. Okay, let's talk about, it's an alternating series, right? How are we going to get it to alternate and start with positive? How about negative 1 to the, and let's start it at 0, okay? Start it at 0. So negative 1 to the n, wouldn't that give us starting with a positive? If we're starting at 0. All right, tell me about, that'll take care of all the alternating. It's always a 1 on top or negative 1. So that should give me all these 1s up here. How about the bottoms? The denominators. These are all factorials, but they're always even numbers, right? So I need to create evens. So we create evens with 2n. Is our first one under here 0 factorial? Yes. So I'll do 2n factorial like that. And then how about the x? X to the 2n. There it is. That is the power series, it's the Maclaurin series for cosine of x. Now, this is where I think things get kind of beautiful, I think. You've heard that cosine x is an even function, right? Cosine of x is even. The property of cosine x being even meant that when you plug negative x into cosine, it's the same as plugging x in, right? That's what was taught in pre-cal. It's an even function. I think now, hopefully, you understand why it's an even function, like where that comes from. Because its power series consists of only even powers, doesn't it? They're all even powers. And therefore, if you plug negative x into this, because they're all even powers, that's exactly the same as plugging in positives, right? So here's kind of like, let's just get to the end of, like, that's our answer, but let's just get to, like, why this is so useful. If I say right now, what is cosine of 2? Let's say we're 2, I'm giving you 2 is in radians, all right? That's going to be a difficult question to answer, isn't it? Without your calculator. If I say what's cosine of pi over 2, that's different because we know these common angles on the unit circle, right? But if I say just what's cosine of 2, you're going to need your calculator to do it, unless you know the Maclaurin series. If you know the Maclaurin series, then all I'm going to do is this. I'm going to plug 2 in for x. So it's going to become 1 minus, let's see, 2 squared is 4, 2 factorial is 2, so this is 4 over 2, right? 4 over 2 is 2. Plus, now what? 2 to the 4th. What's 2 to the 4th? 16 divided by 4 factorial. So remember, this is, you can say 1 times 2 times 3 times 4, right? So when you take 16 and divide it by, let's say, 8, you get 2. And then you still have a 3 down there, so what do you get? Y'all okay? Plug 2 in here, you get 16. Divide that by 4, what do you get? 4, divide that by 2, what do you get? 2, but you still have a 3 down here. So how about what? 2/3? Minus, now what's 2 to the 6th? 64. Yes? So you get 64 divided by 1 times 2 times 3 times 4 times 5 times 6. And you could clean that up, but doing that if you do that on your calculator, we could keep going, right? If you do this, I can guarantee you it's getting closer and closer to what cosine of 2 is. In fact, if you cheat and you just hit cosine of 2 and make sure you're in radian mode on your calculator, this is exactly what your calculator is doing. It's just plugging 2 into this and giving you a result. The question is, when does it stop, right? Like, when does the calculator actually stop? Because this is an infinite series. So it actually stops at a given tolerance that's built into the algorithm when it's computing it. So what it's doing is it's saying it'll compute out maybe the first 10, or like, well, it'll compute like the first one. And then it'll compute the second one, it'll compare them. And it'll say, what's the difference between those two answers? If the difference is big, then it says, let me go to another one. And it looks at the difference between the last two answers. And it says, I'm going to stop going out when the difference between the two answers is smaller than some built-in tolerance in the computer. And a lot of times you get to control that. In your mode feature, there's a float control where you can control how many digits you want it to go out. If you want it to go out more digits, it's going to adjust the tolerance here and make it go out further before it stops. And that's how it gets more significant digits for you. Understand? It has no idea cosine is this curvy looking thing and adjacent over hypotenuse. It has no idea. It just knows how to do arithmetic, right? Beautiful. All right. So that brings me to something that I think is pretty awesome. I just don't know if I should do it. It'll eat up some time. Why don't we take a break? Y'all ready for a break? Yeah? Okay. Take a break. Let's come back, 10 minutes or so. Okay, continuing here, I did not mention, I should have mentioned that because this series is a power series, we could try and find its radius of convergence, right? When would this converge? And if you look at it, this is very much like the geometric series over there, isn't it? X to the n, except we have x to the 2n. So we would need to rewrite this as x squared to the n. And then we would need x squared, the absolute value, to be less than 1. Right? Yes? Or you know what? Let's do it this way. Yeah, I'll get this out of here. Better yet, it's not geometric because of all that crap out front. I'm not going to go through the work. I'm just going to show you what you would do. To find capital R, radius of convergence, you would do ratio test on this. Remember what the ratio test was? Limit n goes to infinity. You plug n plus 1 into this, divide it by plugging n into this, and you need that less than 1, absolute value. Do all that. If you did it, you would find that the radius of convergence is infinity, meaning that it converges for all x. So it does not matter what x you plug into this, it will always work. So you can always use this power series to evaluate cosine for all x values, okay? Now, let's just do sine x, because it works pretty clean and pretty easy, same way. Find some derivatives. What's the zeroth derivative of sine? Let's try and do it all at one time. at 0. I'm doing the Maclaurin. What is the 0th derivative of sine, and then plug 0 into that? So what's sine of 0? 0. Okay. What's the first derivative of sine? Cosine. Plug 0 into that. 1. What's the second derivative? Be negative sine, and then plug in 0. You get 0. What's the fourth derivative? Negative cosine, plug in 0, you get negative 1. Do you understand what I'm doing there? No? Was that too much? Too fast? Okay? Oh, third, yes. Thank you, thank you. And then what's the fourth? We're going to start repeating, right? 0, then 1, then 0, then negative 1, then 0, then 1, then 0, then negative 1. That means that sine of x can be rewritten as the sum n equals 0 to infinity of the nth derivative at 0 over n factorial x to the n, which would be, now let's go through these again. Plug in 0, what do you get? 0 over 0 factorial x to the 0. Plus, what's your next one? 1 over 1 factorial x to the first. Next one, 0 over 2 factorial x to the second. Next one, negative 1 over 3 factorial x cubed. And now we start repeating the pattern. 0 over 4 factorial x to the fourth. 1 over 5 factorial x to the fifth. Yeah? Plus dot, 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 dot. Lots of things cancel. All the what? All the even powers cancel, right? Which means you're going to be left with just the odd powers. Oh, isn't sine an odd function? Sine is odd? That's why. So the power series would be, or the expansion of the power series would be x and then minus 1 over 3 factorial x cubed, then plus 1 over 5 factorial x to the fifth. What would be the next one? Minus 1 over 7 factorial x to the seventh. One more. 1 over 9 factorial x to the ninth. The next one would be minus 1 over 11 factorial x to the 11th, blah, 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 blah. So let's write this in its format. Sum n equals 0 to infinity. All right. We need alternating series starting with positives. So negative 1 to the, in this case, n plus 1, because we want the first one to be positive, don't we? Wait, hold on. No, just n. What was our last one? Oh, because it was 0. And did we do that one right? Hold on. I'm doubting myself here. It was, hold on a second. Hold on a second. When we plug in 0, we get 1. I mean 0, right? Which can give you 1. When we plug in 1, we should get negative 1. Yeah, this is right. Okay. It's starting with positive. So I don't know why I thought we did that wrong. Okay, this one's going to start positive also. And then negative. So on the bottom, what? We want odds, right? Odds starting with what's down here? 1 factorial. So how do I create odds starting with 1. 2n plus 1 will create the odd numbers starting at 1 and then factorial. Do you all agree? Because I'm starting at 0. So plug 0 in here, you get 1 factorial. Plug 1 in here, you get, what, 3 factorial. And then plug in 2, you get 5 factorial. And so on and so forth. And then x to the what? 2n plus 1. Same thing. Create the odds starting at 1. We good? How would you find the radius of convergence? Ratio test. Not going to do it. But if you did ratio here, you would get that r is infinity also. And so this works for all values of x. All right, I'm going to show you another one. And then I'm going to show you something I hope that you'll think is cool. I don't know. Do y'all still need that? No? Good. How about find the Maclaurin? And the radius of convergence for e to the x. Well, this should be easy, because all the derivatives are the same, aren't they? What is the 0th derivative, and then plug 0 into it? 1, right? First derivative, plug 0 in. Well, derivative e to the x is itself, so plug 0 into e to the x again, you get 1. So all of them are 1, aren't they? They're all 1s. Which should make writing out this series pretty easy. F of x, e to the x, should be able to be written sum n equals 0 to infinity of the nth derivative at 0 divided by n factorial x to the n. And if all of these guys are 1s, then it's just going to be 1 over 0 factorial x to the 0 plus 1 over 1 factorial x to the 1 plus 1 over 2 factorial x to the 2 plus 1 over 3 factorial x to the 3 plus ... Which is just what? 1 plus x plus 1 over 2 factorial plus x squared plus 1 over 3 factorial x cubed plus ... Yes? Understand? And if we write that as a power series, it's just 1 over n factorial x to the n. That's it right there. Doesn't alternate, so we don't have to worry about that. The bottoms are always factorials. The powers on x just keep going up by 1. And that's your power series. Now, check this shit out. This is pretty cool. I think this is cool. You were told a long time ago that there's this function out there called e to the x, right? And it's a very special function because it is the only non-trivial function that is its own derivative, right? Take derivative e to the x, you get itself. Yes? And we are saying that e to the x is actually this, right here. Yes? What is the derivative of this? So what's the derivative of 1? 0. What's the derivative of x? 1. I'm going to write that down here, 1. What's the derivative of this? So 2 comes out, cancels out, and you just get x, don't you? The next one, the 3 comes out, cancels just the 3 on the bottom. What's still on the bottom? 1 times 2, which is 2 factorial, and then x to the second. The next one, even though I didn't write it out here, a 4 would have come out, canceled with the 4 from the 4 factorial, would have left you with 1 times 2 times 3, and so you would have had 1 over 3 factorial x to the third. And it kept on going. And that right there in blue is exactly this blue box. It is itself. The only function that does that, other than f of x equals 0. The constant 0 function, the derivative of that is itself. But that's a trivial, that's, who cares about the constant 0 function? It doesn't do anything, right? So that leads you to something like this. If we wanted to integrate this, this is not integrable, meaning there is no technique of integration for this. Nothing we can do. And this is where I was telling you a while back that, the two fathers of calculus, Leibniz and Newton, had different versions of calculus. A lot of it was the same in different notation, but Newton had the power series, Leibniz didn't. So if Leibniz were faced with this problem, he'd be like, no go. Newton would do this. Newton would say, all right, I'm going to integrate this, but I'm going to rewrite e to the negative x squared in its power series. So he looks at this, and he goes to the formula we just got right here, right? Here's our formula in this box. And this is what e to the x is. All I'm going to do is use that formula, but instead of using x, I'm going to use what? Negative x squared. So I'm going to plug, this is like e to the x, but I'm replacing the x with this. So in this box, replace all these x's with negative x squared, and you would get 1 plus negative x squared plus 1 over 2 factorial, what, negative x squared, what, squared, plus 1 over 3 factorial, negative x squared, cubed. Understand? Plus dot, dot, dot. And then, I'll clean it up. 1 minus x squared. What happens when I take negative x squared and square it? It's to the 4th power, isn't it? And it's positive because you're squaring a negative. So this is plus 1 over 2 factorial x to the 4th. Now what about the next one? When you take negative x squared and cube it, you get what? Negative x to the 6th, right? So I'm going to turn this into a minus 1 over 3 factorial x to the 6th. And then I could keep going, couldn't I? And could you integrate this? Term by term, couldn't you? So let's do the integration. It'd become antiderivative of 1 would be x minus 1/3 x cubed plus 1 over 2 factorial times 5 x to the 5th minus 1 over 3 factorial times 7 x to the 7th plus dot, dot, dot plus a constant, right? It's just power rule on each of these. And so that is a new power series, and that is the antiderivative. And so if I'm doing a definite integral now, and you give me numbers, right, here from somewhere to somewhere, then all I need to do is just first plug that top one in here, right, figure out what it is, plug in the bottom one. Now, of course, I can't go forever, so the sacrifice is that at some point you have to stop, and that's what I was telling you. You stop wherever you're within the tolerances of what it is you're trying to get, right? Building aircraft bearings, or are you building a wooden toy set? You know, just tolerances are different for different things. Do you see the power of this Taylor-Maclaurin series? Okay. Now, on page 484, there's a table on this page that has a list of the common Maclaurin series. It has 1 over 1 minus x over there. We know is, sum x to the n. And next to it, it shows the radius of convergence. And then it does e to the x's here. Then you've got sine x, cosine x, arctangent x, natural log 1 plus x, and then 1 plus x to the k. These are the common known Maclaurin series so that you don't have to derive them. And what happens is that later on, we don't go and find the Taylor series, or we don't find Maclaurin series. What we do is we just refer to a table. We say, oh, okay, yeah, let's look up the Maclaurin for that. As long as it's a common function, we just go right to the table. All right? But that's where they come from. So just be aware of that, the table for common. You don't need to memorize them. Just know it exists. Now, I'd like to show you something that, again, I'm hoping is going to pique your interest. I don't know. How many of you have ever seen this? It's argued to be the most beautiful equation in math. I'm not telling you it is. When I was shown the first time, they told me the same thing. Like, people think this is the most beautiful equation in math. It's a version of it. Most beautiful equation in math. I'm going to put a question mark next to that, all right? Here it is. E to the I pi plus 1 equals 0. How many of you have ever seen that before? One? Okay, good. Then for a lot of you, this is brand new. E to the I pi. E to the I pi plus 1 equals 0. That equation is true, okay? That is true. If you move the 1 to the other side, it just means e to the I pi is -1, right? That's really what this is saying. But we move the 1 to the other side because it makes it a little more beautiful. Now, let me tell you why it's argued to be the most beautiful equation in math, all right? First, it contains the number 1 in the equation. Now, how important is the number 1? Well, we call it the multiplicative identity in our number system, right? You multiply anything by 1, it's itself, right? So we have this property that x times 1 equals x. That's a very, very powerful thing to have in a number system, a multiplicative identity. It's one of the 12 things that are required to have what's called a field. All right, so there's the multiplicative identities there. Then we have the very important number 0, which is the additive identity, which means that anything plus 0 is still itself, right? Then it contains this wonderful number pi, which was this mysterious thing. It evaded us for so long. You take any circle, you take its circumference and divide it by its diameter, and you get pi all the time. No matter how big your circle is or small, the ratio of the circumference to the diameter is always pi. So that was this very, very nice thing that we had, circumference over diameter for a circle. Then we have, I'm doing these kind of in the order that you're exposed to them. E, right? E is this, it's just a number, 2.714, but it's this very, very special number that if we use that number as the base of the exponential function, it is the only one that is its own derivative, which we just showed a second ago. So that number is critically important to us, right? It's harder to define what E is, so I'm just going to say, did we do it with the limit in here? Did we show what E was? No, that's more of a Cal 1 thing. E is approximately 2.714, but it is that base for the natural exponential function. And then finally, we have I. I is this thing that's got this bad reputation, right? I is defined to be the square root of -1. It's the imaginary unit. It's the number that when you square it, you get -1. I squared is negative 1, right? That's what we got from this. Now, a lot of times in a college algebra class, you don't spend too much time in this. You just kind of are introduced to it. You've seen it, but you don't really get too deep into imaginary numbers, right? And you really wouldn't ever see it even if you take Cal 3 and differential equations. And really, the imaginary number doesn't come back again until you take a class called complex variables. And what happens in complex variables is that all these functions that we've studied, you know, f of x equals x squared, sine of x, now instead of only allowing yourself to plug in numbers, real numbers, you're now allowed to open it up to imaginary numbers. And that creates this whole new realm of functions. And the calculus in there is more complicated because the numbers that are imaginary, you need 2 dimensions to visualize them. And so things get hard to visualize when you try and graph functions. I'm not going to get too far into it. All right. So that equation connects all of those beautiful numbers together, all those very important numbers together in one simple equation. So I'm going to show you why that's true. Okay? Here we go. I'm going to show you why the equation is true. Do you agree that it would be enough for me to show you this? If I show you that, would you agree with me? Yes? Okay. This can be pretty easy to do. Because e to the I pi, according to the Maclaurin series, this right here, oh, you know what? Let's do this. I'm having some issues here. Come on, stop. Let's do this. I'm not going to plug pi in. I'm going to say e to the ix. What is e to the ix? So the part up here is the part I'm replacing, right? That's like the x in the formula. So according to our little expansion of e to the x, this should be 1 plus what? Ix plus 1 over 2 factorial Ix squared plus 1 over 3 factorial Ix cubed plus 1 over 4 factorial Ix to the 4th, maybe 2 more, 1 over 5 factorial Ix to the 5th plus 1 over 6 factorial Ix to the 6th plus dot, dot, dot. Y'all agree? Clean up. Equals 1 plus Ix. Tell me about this next one. What happens when I square I? Negative 1, right? Negative 1. And then square x, I get x squared. So this is going to turn into negative 1 over 2 factorial x squared. Yes? All right. What happens when I cube I? So what's I cubed? So here's I cubed. That's I squared times I, isn't it? I squared times I. What's I squared? Negative 1 times I. Would you agree that that's negative I? I cubed is negative I? All right, so I'm going to have a negative I and then x cubed. So I'm going to write it this way. Negative 1 over 3 factorial I x cubed. Do y'all follow that? Next one. What is I to the 4th power? That's I squared times I squared. I squared is negative 1. I squared is negative 1. Negative 1 and negative 1. Positive 1. So I get plus 1 over 4 factorial, what? X to the 4th. Okay. How about the next one? What is I to the 5th power? I'll do it up here. I to the 5th. This is I to the 4th times I, isn't it? What's I to the fourth? 1. We just said it was 1, and then times I, so just I. So this one is going to be 1 over 5 factorial. There's going to be an I and then x to the fifth. What's the next one? What's I to the sixth? That's I squared times I squared times I squared. So it should be negative 1. So I'm going to have minus 1 over 6 factorial x to the sixth. And I could keep going, couldn't I? Yes? Do you want to write the next one? I think this might be enough for you to see what happens here. I'm going to highlight everything that doesn't have I. Do you recognize that? 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth. Do you recognize that? What is it? What is it? I hear it. This is all I hear. We just did it. It's cosine x, isn't it? Isn't that cosine x right there? Okay, now I'm going to highlight the stuff that has i's in it. And since these all have i's in them, can't I factor an I out? Yes? One I out of each one. So I could put plus, here's an I. And now what, just imagine this now without the i's. What is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth, blah, 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 blah. Sine x. And this right here is called Euler's formula. It's saying that if you want to take e raised to an imaginary number like this, what you will do is you will take cosine of this x plus I times sine of the x. Very, 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 very important formula in mathematics. And using Euler's formula, remember what I was trying to convince you of. What is e to the I pi? So replace your x with pi. Cosine pi plus I sine pi. And what is cosine of pi? Negative 1. Plus I times what is sine of pi? 0. So the answer is negative 1, which is what I was trying to show you, right? That's what I wanted to prove. So e to the I pi is that. Interesting. I'll show you a problem that you can give to your friends to try and stump them, all right? Your friends who like math, okay? Don't give this to your friends that don't like math, because they'll tell you to, well, I don't know what they'll tell you. I can only tell you what they tell me back in the day. All right, so someone tried stumping me with this once. What's I to the I? What's I to the I? I raised to the I power, right? That's weird? That look weird? Okay, so what I'm going to do first is I'm going to use Euler's formula, and I'm going to work backwards for a second. Because this is not a class where we could fully introduce you to this whole topic, so I'm going to do this kind of by reverse engineering it. How could I get just this I to pop out right here, and this to go away, and this to become something that just leaves me with I? Sorry, this one right here. I just want I to be right here. What could I plug in for x that would make this go away and this just turn into an I? Pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So you would get I, wouldn't you? Ah, that's the key. Because that means that I is actually equal to what? Cosine pi over 2 plus I sine pi over 2. But that's just e to the what? I times pi over 2, right? I times pi over 2. So what I'm going to do is I'm going to take this and I'm going to rewrite the base I as e to the I times pi over 2. And then I'm going to take that, because that's I, right? And I'm going to raise it to the I, but I'm going to leave that I alone. I'm not going to touch it. And what happens when you take something to a power to a power? What do you do to the powers? Multiply them. What's going to happen when I hit I times pi over 2 with I? I times I is negative 1. So you get e to the negative pi over 2. And that is now a real number, and you can actually just type that into your calculator. But the exact answer is this. So I to the I is e to the negative pi over 2. Most people have not seen that, even if they've taken calculus, because a lot of calculus teachers won't go into this part. I just think it's cool. So all of that was dependent upon our understanding of the Maclaurin series for e to the x, right? Rewrote e to the ix as its expansion, then realized cosine and sine were in there, and that gave us Euler's formula. Euler's formula, some people pronounce it Euler's formula, but right, have you heard Euler before? Yeah, it's Euler, right? I mean, but then I've also heard like different debates on it. It's supposed to be Euler, but doesn't matter as long as we know what we're talking about, right? All right, 11:30. How are y'all feeling? I mean, I know it's this almost the last day of class, but are y'all even excited about this stuff? Were you ever excited about this stuff? No answer, of course. Did I tell y'all that I'm making these videos for an internet class? Did I tell y'all about that? I did or no? Oh. Yeah, I'm saving the videos, but what I'm doing is we're going to try and offer Cal 2 for the first time this upcoming semester online. And so the requirement from my students is going to be that they have to watch the lectures. And I have this class, and I have 2 or 3 other semesters of classes that they can go back and watch. And so, I mean, it's better than most internet classes where they just give you a book and they're like, you know, good luck, go learn it. You know, at least they'll have something to refer to. But I appreciate your enthusiasm this summer. It should carry over well into the videos. I mean, I hope that they'll be able to pick up on it, you know, on how excited you were. I mean, to my internet students that are going to watch this possibly, you can't imagine the elation in this room right now. All right. All right, find the Taylor series here. Taylor, that's not Maclaurin, right? So this time the A is given to us. This is another way they can say it. Instead of saying centered at something, they can say about something. And I gave that to you before in your notes when we were talking about series. We were talking about the, when we first started Power Series, we said it's either centered at or about. 2 different ways of saying the same thing. All right, so we need derivatives, don't we? We need derivatives. Unfortunately, this derivative is not nice, so I'm going to go a little slower. The 0th derivative at x, I won't plug in 3 yet, is itself. Great. What is the first derivative? 1 over x. Now I'm also going to write that as x to the negative 1, just because it'll help me get derivatives as we proceed. What's the second derivative? It's negative x to the negative 2, which is negative 1 over x squared, but I'll put the other version of it right here. All right, so I'm just using power rule on these. What's the third derivative? Yeah, I hear you. What's the third derivative? So positive 2x to the negative 3, I'll put that out here. 2x to the negative 3. And over here you said it would be 2 over x cubed. You're going to see here in a second, we're going to actually prefer to work with this one when we write our formula out. These are not getting any nicer, are they? They're not going away. They're not repeating themselves. But we can continue to do this indefinitely, right? We're never going to run out of derivatives. What's my next one going to be? Negative 6, but it's 2 times 3. Do you think that might become important to us? Yeah, we probably want to leave it as negative 2 times 3, x to the negative 4. Because the next one's going to be, what, 2 times 3 times 4? Yes? So the fifth derivative is, what, positive this time, right? 2 times 3 times 4, x to the negative 5. And I think you can start to pick up on a pattern here, can't you? What's the sixth derivative? Two times 3 times 4, oh, negative though, right? Negative this time? Times 5, x to the negative 6. And I could keep doing this, right? And then what I'm going to do is I'm going to be plugging 3 into this, right? Plugging 3 in. Let's first, though, try and come up with a formula. What would the nth derivative be? Can anyone tell me what the power on the x will be? So for the sixth derivative, what was the power here? Fifth derivative, fourth derivative, right? So this should be x to the negative n. And then tell me about the number in front here. 2 times 3 times 4 times 5. 2 times 3 times 4. It's n minus 1 factorial. Looks like what's in front of this. That's multiplication right there. And then it alternates in signs, doesn't it? The first derivative was positive, second. What about the zero derivative? It was, there's a little bit of a trouble here. Hold on. Does this formula work for 0? Look at this. Does it work for 0? When I plug in 0, I'm supposed to get natural log x, right? It doesn't work for 0. So I need to keep that in mind. This works for n bigger than or equal to 1. For 0, it doesn't work. It fails. So the pattern only starts at the first derivative and on. So if I'm going to have to start at 1, right, then I need my first one to be positive, then negative, then positive, then negative, then positive, then negative. So how can I make that happen? Starting at 1, I need it to be positive. So n plus 1. All right with this? No questions? All right, let's go back up now and let's plug in our a. So when we plug in 3, what would be the 0th derivative at 3? Natural log 3, right? And then the rest of them I have a formula for, don't I? Don't I have a formula for it? So let me go down to my formula. It'll be -1 to the n plus 1 times n minus 1 factorial over 3 to the n. So what I did there is I realized x to the negative n, just drop it down to the bottom, and I'm replacing x with 3, yes? So that is the formula for the nth derivative evaluated at 3. So this is the formula for the nth derivative evaluated at 3. That's what that is. But it only works for what? N bigger than or equal to 1. All right. We have the construction of what we need to now write the Taylor series. Okay? Here comes the Taylor series. The Taylor series for f of x equals natural log x about x equals 3 is now we know it's this sum, right? But our sum and our formula only work for n is bigger than 1 or bigger than or equal to 1. So this is the original formula. It starts at 0. What goes here? This is the nth derivative at a, which is 3, over n factorial, and then what goes here? X minus 3, good, to the n. So when I plug in 1, what do I get? When I plug in 0, what do I get? What was the 0th derivative at 3? What was it? It was ln3 over 1. So 0, I'm going to put 0 factorial still. And then x minus 3 to the 0. Plus. Now, from here on out, I have a formula, don't I? From here on out? At 0, I didn't, but from here and continuing forward, I have sum n equals 1 to infinity. And what was my formula for that part here? -1 to the n plus 1 times n minus 1 factorial all over 3 to the n, right? But I still need to divide that. That was just this piece, right? I need to divide that by what? Right, look at my formula right here was for the nth derivative at 3, right? That was my formula. But in the formula for Taylor series, I have to take that, whatever it is, and divide it by n factorial. So when I divide this by n factorial, isn't that the same as just putting an n factorial down there? I'll highlight it because I don't want you to forget it. That n factorial came from this right here in the Taylor. And then I'm still not done with the Taylor. What still needs to be thrown on the outside of this? X minus 3 to the n. Is there anything we could do with those factorials to clean them up? Yeah, couldn't I take this one and peel off an n and write n minus 1 factorial? And then wouldn't those n factorials cancel? And you just have an n down there? If we do that, that'll give us our final result. So I'm going to continue this on the next page. The first term is natural log 3 plus sum n equals 1 to infinity of negative 1 to the n plus 1 over what? 3n times n, or 3 to the n times n. You could do that several ways. I'm going to write it this way. And then x minus 3 to the n. That's your Taylor series. Everybody recognize this part right here, C sub n. This is x minus a to the n. I mean, a Taylor series is a power series, and all power series have to look like that thing way over there in the box. So we do have some constant term that's being manipulated by n, and then we have our x minus a to the n. We do have one term out here that we had to keep track of, but that was only because that formula didn't work that first time through. But it's okay, it's just one term added to an infinite sum. It's fine. This might be loud, so be ready.
It seems that you are not.
I'm gonna. Oof. All right. So see, are we in the same section? We might be out of this section. No, we're still in the same section. Multiplication, division, and power series. So we've seen already that if you have two power series and you want to add them together, we did that earlier today, you just have to make sure the indexes are the same, and you have to make sure you have like x to the n in both of them, and then you can put them together. But multiplication, not so easy. There's a lot more involved. So let me give you your first example. Find a power series for f of x equals e to the x sine x. Use tables. On your exam, your final, I will provide you with the tables of the common Maclaurin series, so you won't have to reference them. The one on page 484 I told you about, I will provide you a copy of that. So this is not about you doing what we just did, where you have to find all the derivatives and come up with a formula and all that. You don't have to do that, but you have to know what the formula is and then put these two together. So this is multiplication, yes? Right between those two. And so what I'm going to do is I'm going to rewrite e to the x as its power series. What is the formula for that? Sum n equals 0 to infinity of 1 over n factorial x to the n. Yes? And then multiply that times sine x, which was sum n equals 0 to infinity negative 1 to the n over, what was it, 2n plus 1 factorial x to the 2n plus 1. Someone double check that. Oh, I've got my table right here. Yeah. Okay. That's what we want to multiply together, right? And you cannot put those two right together. Like, okay, you know, just put this next to this one inside of a sum. I showed you that last class, that when you do the multiplication that way, you miss a bunch of stuff. All right, so now what we'll do, and this just gets kind of tedious, is we're going to write out the first few terms of each of these series. We know that the e to the x one, if we plug in 0, then 1, then 2, then 3, we get 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth plus dot, dot, dot. And then when we do the one for sine and write out the first few, we have x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh plus dot, dot, dot. And now we have the pleasure of actually expanding this. So you remember how to do expansion? You start with the first one here and you multiply there, first one then there, first one then there, first one then there, right? And then you move to the second one and do the same thing, and then the third one, and then the fourth one. All right? That's what we're going to do. So as you can imagine, this could become a nightmare. And so a lot of times, in fact, all the time on the instructions for a problem like this, I'll say something like, find only the first 3 terms. Okay, so we'll only want to find the first 3 terms. I didn't say that in the beginning because it wouldn't have made a whole lot of sense what I'm talking about. But now you can see that when I multiply this through, when I do my first multiplication, I'm going to get what? X, right? Then I'm going to get an x to the third, then an x to the fifth, then an x to the seventh, right? With some numbers in front. And then when I come through with my next multiplication, I'm going to get a what? X squared, x to the fourth, right, term, and x to the sixth term. So what we're going to want is to have the first 3 terms accounted for. That means, I don't think there's any way we can get a constant, can we? Just a constant? I don't see. The lowest power of x we're ever going to have is what? 1, just x to the first power. And the highest power, it's just going to keep going, so we don't have to worry about that. So we're going to want an x term, an x squared term, an x cubed term. If we get just those first 3 terms, we're happy, we can stop. All right? Understand that? You got to kind of know when you stop. So if I know that I'm just going to need an x term, an x squared term, x cubed, then I don't need to come all the way out here to this one, do I? All right, so let's do the first multiplication. I pass a 1 through first. I get x minus 1/3, or 1 over 3 factorial, x cubed plus 1 over 5 factorial. You know what I should have done? You know what? Come back. Hold on. Leave some space. Leave some space. Because we didn't have an x squared in there. This just helps you keep track of things. Okay. That would be my first multiplication through, wouldn't it? Yes? Now, I could keep going with that. Then what I want to do is add to that my x being passed through. So what's x times x? X squared. I'm going to put that below this in a separate row. And so at the end of the day, I'm just going to add everything down, straight down. So x squared is going through here. That's this one times this one. Then x to the x times this one, which would give me what? Negative 1 over 3 factorial x to the 4th. Is that all right? That's x times this one. It's right here. I'm doing like rows. The first multiplication through is my first row. The second one is my second row. The third multiplication through will be my third row. And I'm just lining up like terms on top of each other. Where? Where? This? Oh, I forgot to put the x to the third. Oh, that's what you're talking. Oh, yes, of course. Sorry about that. Should I go any further? I shouldn't need to, because the first three terms are only going to come from these three, right? X squared, x cubed. So I should be okay with that. Let's move on to the next one. X squared is going to go through to this one. What is that? 1 over 2 factorial x cubed, which I'll line up under here. 1 over 2 factorial x cubed. I think I want to move this a little bit to the side. It's kind of in my way. Do y'all see I'm trying to line these up into like columns? And then what I'll do is I'll just add them down when I'm done. Should I go further out? Should I do this one times the next one? That's going to give me a 5th power of x, right? I don't need to go that far. How about the next one? How about the this one through to here? That's going to be 4th power, and that's bigger than what I need, right? Now, had I said go 4 terms, then of course you would have had to account for all this. But since all I'm focused on is what's happening in these first 3, then no matter what I do next, right, as I keep moving out, everything's higher than 3, isn't it, power-wise? So I can actually just forget the rest and focus just on those and add those together. So I have in the x column, I have just x. In the squared column, I have x squared. And then in this one, I have plus, now watch the way I write this. You can go either way. I'll do 1 over 2 factorial minus 1 over 3 factorial x cubed. So all I did was like looked at the coefficients of the x cubed. The coefficient of this one is negative 1 over 3 factorial. That factorial should be down with the 3. 1 over 3 factorial is the coefficient here. 1 over 2 factorial is the coefficient here. I put these two together. I just changed their order. I put the positive one in front of the negative one. And then I say plus dot, dot, dot. Okay? That's it. That seem okay? Reasonable? You could figure out what that is. I mean, for this one, it's what, 1/4 minus 1/6, so you figure that out. Yeah. Ready for another one? That was multiplication. Multiplication is a lot easier than division. Find first, how many terms should I go? 3 terms. Of power series for f of x equals 1 over sine x, which is cosecant x, isn't it? The only thing I know is the power series for sine, right? That's all I know. So I'll rewrite this as 1 over, what is the power series for sine? This time I'm not going to write in the sigma notation. I'm just going to write out the terms. So what was it? Start x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus dot, dot, dot. Do you agree? It has them both. The table has the sum written, and then it has like the first 5 or 6 terms written. So it's nice, you'll be able to just write it down. All right, now, you can't just put 1 over x and then 1 over the next one, right? Because there's more terms on the bottom, multiple terms, and there's only 1 on top. So guess what you get to do? That's a drum roll. Long division. You get to do long division. So this equals, and give yourself plenty of room here, what goes inside the division box is the numerator, right? 1. What goes on the outside is the infinite polynomial. And so I'm going to put it out here, x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus dot, dot, dot. Understand what I'm doing? Now what we did with long division is we always looked at the number, the thing out here, right? And we said, what do I have to multiply to get it to turn into this? Yes? And we always said we would stop long division with polynomials whenever the power here was less than the power here. So we would normally just stop. Not now. You can turn x into 1. How? 1 over x. Multiplied by 1 over x. Right? What's x times 1 over x? It's going to be 1. So I'm going to put 1 over x up here. You okay with that? And now what did you do after you figured out what that thing was up here? You multiply that times this, don't you? And you line that up under here, and you subtract. So what's 1 over x times x? 1, I'm going to put that here. I'll subtract at the end. What's 1 over x times this? It's just going to reduce the power by 1, isn't it? So it's going to give me an x squared term. Now this is a constant. I'm going to line up a column here for my x's. I'll even put a little thing here. This is my constant column. This is going to be for my x's, then my x squareds, and then my x cubes. So when I multiplied this 1 over x times this, I get negative 1 over 3 factorial x squared. I'm going to put that in my x squared column right here. Negative 1 over 3 factorial x squared. Y'all okay with that? Then let's go again, because I don't know how many of these I'm going to need. Do this times this. That'll give me a plus 1 over 5 factorial x to the 4th, and I'm going to put that over here in a column. Plus 1 over 5 factorial x to the 4th. Yes? Now we come through and subtract this row. So subtraction changes the signs, changes that minus to a plus, changes that plus to a minus. So I over-exaggerate it so that you can see that the sign changed. And then add down. What happens when you add down? 1 over 3 factorial x squared. And then over here, minus 1 over 5 factorial x to the 4th. And now we repeat the process. What do you multiply x by to get 1 over 3 factorial x squared? 1 over 3 factorial x. That's my next term. Plus 1 over 3 factorial x. Right? If I multiply this times this, I get this, and that's what I want. So I go ahead and now distribute this through here to here. I know that that's going to give me the 1 over 3 factorial x squared I need. But then what's my next term? This one times this one right here. What do I get? Negative, right? 1 over 3 factorial times 1 over 3 factorial again. Yes? So negative 1 over 3 factorial times 1 over 3 factorial x to the 4th. I don't think I'm going to go any further. I think that's good enough. I mean, further on this multiplication. Do we have a question on this? Do y'all see why it's 1 over 3 factorial times 1 over 3 factorial? Because they both had them, right? This had them, and this had it. And it was negative because one's positive, one's negative. All right, let's bring in our line. Let's subtract. Changes the signs. And what pops out of the bottom right here? You have to add those together, don't you? Oh, goodness. Well, when you add these together and they have the same power, you just add the coefficients. So could I write it like this? Could I say that this is 1 over 3 factorial times 1 over 3 factorial minus 1 over 5 factorial x to the 4th? Could I? It's the coefficient of this one, then take away this because it's minus, and then x to the 4th right next to it. I could figure out what those are, right? That's 1 over 6 times 1 over 6. So that's 1/36 minus 1 over whatever 5 factorial is, right? And I'll get that number in a second, but do you understand what I've done there? No? Okay, now what do I need to multiply x by to create this? So I need x cubed, right? But I also need this coefficient. So this will be plus 1 over 3 factorial times 1 over 3 factorial minus 1 over 5 factorial x to the what? 3rd plus dot dot dot. Why am I stopping? I'm not even going to multiply it through. Why am I stopping? I've got the first 3 terms. Right? I've got the first 3 terms. So that up there is my answer. Now, if you want to go figure out what this is, you know, like I said, 1/6 times 1/6, 1/36 minus, what is that, 6 times 4, 24. You could get your common denominator, subtract, and done. So you would box this up right up here with your little dot, dot, dot at the end, and that would be the power series. The first 3 terms. So let's revisit this. You want to kill the lights again so we can go to sleep? Let me get back to where this was here. I'm looking for where he points up at the board here. Right up here. I think that's it. Back it up. All right. So to the best of what I can make out on this, these don't go. You can't put these. Can I borrow your crutches? Can I borrow your crutch? One of your crutches? I just need a pointer. This will work. Thank you, sir. So look right here. It's 1 divided by, I think that's like an x cubed or something. And then this right here is a power series because this is plus dot, dot, dot. That's what he has written there. So right here, this is a power series. So on the next step, the 1 over x, I think, cubed, that's just 1 over x cubed. That's right here. And then this whole thing, right, 1 over this whole thing turns into this. And the question is, how does this step go from here to here, right? What did they do? What did he do? He took 1 and divided it by an infinite series, and it turned into this. Now he went out 1, 2, 3, 4 terms, then plus dot dot dot. So he went out 4 terms on it. Do you see it? Thank you. Glad you hurt your foot. I'm just kidding. Is it all right? Yeah, okay. So if we play back his answer to their question,
From here to here.
we can have somewhat of a different appreciation for it. Yeah, I know. What's what? You leave it like this?
Divide 1. From here to here.
Yes.
Or you can divide 1.
Oh, you can divide 1. That's what he's saying, right? That's exactly what he did. Oh, you can divide 1. You divide 1 by what? By that infinite series right there. You divide 1 by that infinite series, and you get this. You see? So, as a student, moving ahead, you should be prepared for this sort of thing because there are a lot of assumptions made that you understand a step. And it is your task, when you don't understand that step, to make sure you go understand it. Don't be a student who's going to blame the instructor for your lack of knowledge. That's not something that was taught in this course. That was a prerequisite for this course, I'm sure. So it's kind of like me going back and trying to explain how to take derivatives in here, right? Chain rule, like that's not something I cover in here, right? We're not going to show you how to take the derivative of a composition of a function because that's assumed knowledge. All right, so I think that that's a pretty eye-opening thing. I'm still trying to figure out what class this is. Looks like differential equations. Yeah, I can't really tell. It could be a lot of different things. 12:17. What time do we end? 12:30. 13 minutes. I'm looking for a homework assignment here. We are actually going to say we're officially done with Chapter 8. Okay? Page 487. Five, 7, 9. Now on these problems it says find the Maclaurin series. That means A is 0. Using the definition of a Maclaurin series, meaning you have to come up with the formula and do it all yourself. If it said using the table, then you would go to the table. You know what? Let's change that 9 because it's a hyperbolic. You already have a sign there. Just for practice here, 5, 6, 7. Then 14 and 15. Those are find the Taylor series, and they give you where it's centered. Okay, so all of those you have to grind out the answers. Then number 31. That you're allowed to use the table on. They tell you that in here. 43 is where they want you to evaluate an integral. They want you to do an integral, but you can't do any technique. So you have to convert the inside of it to a power series and then write out the terms. It's an indefinite integral, so you're just going to leave it unevaluated. Does that make sense? Find the antiderivative. It'll be a series. You just leave it like that. And then you need some practice with the multiplication and division. So where can I give you something like that? This is set 8-7, yes. How about 55? Well, 55 is so close to what we just did, but that'll be good. And then 56. And on 56, just a quick little hint on 56, you're supposed to find the Maclaurin series for secant x. Just remember, secant x is 1 over cosine, and then just do it the way we just did 1 over sine. Just a little different in the numbers. And I think they ask you for the first 3 terms. First 3 non-zero terms. All right, so what is our plan going ahead? We're kind of done with the series. What's for next week? We're going to get into Chapter 9. We'll see how far we can get in one class. My guess is we'll be able to get an introduction into parametric curves and spend the first half of class on that. And then after that, we'll do polar coordinates. And it's going to be a very informal sort of like, here's polar coordinates, practice with them a little bit, and then here's the calculus we can do with them. Here's a formula for area, here's a formula for arc length, without actually setting it up how we did all the other formulas where we took our time to draw pictures and find out what slices look like. It's going to be more of like, well, here it is, here's the formula, let's use it. All right? That'll be it. So we'll finish somewhere next class, 9-2, probably 9-3. Okay? Do your homework. Have a good day.